lectures, we were discussing the so-called convergence theorem. Okay. And at the end of last lecture, I just hinted at the fact that bounded convergence theorem is a special case of dominated convergence theorem. And I thought of leaving it to you, but let me start by stating precisely what is bounded convergence theorem. And proof is just a single line because it follows from dominated convergence theorem. So for the sake of completion and record, what I will do is to start by precisely stating the last convergence theorem that we have in that list, namely bounded convergence theorem. The statements goes as follows. Let sequence Fn be a sequence of measurable functions. Like in dominated convergence theorem, there is no assumption of non-negativity here. Defined on a subset E of R with finite measure. So that's an additional hypothesis that we have compared to other convergence theorem. So we are talking about only those functions which are defined on a measurable subset with finite measure. Okay. Further, as the name suggests, we are going to handle only bounded sequence. Modulus of Fn of x is less than or equal to m for all n in n almost everywhere on E. Not for all x in E, but for almost all x in E. Those x in E for which this inequality is not true is of measure 0. Further assume that Fnx converges to Fx and Fnx converges to f of x almost everywhere on E. Then the theorem asserts that f and fn are all integrable. And further, integration process is a stable process with respect to limit. Integral of f dm is equal to limit n tending to infinity integral of f and dm. Integral over E, where E is of finite measure. Okay. So the additional assumption is that the sequence is defined on a set of finite measure. As I told, the proof follows from dominated convergence theorem. Do you see that dominated convergence theorem can be applied? Please recall the statement of dominated convergence theorem. What you want there is, you want a single function such that every function in the sequence dominated by that single function, and that single function should be integrable. Modulus of fn of x is less than or equal to g of x, and g of x should be integrable. Then you can apply dominated convergence theorem. Are you in that situation?
Yes, sir.
Yes, sir.
Instead of g, you have a
Constant function.
constant function. Whether a constant function is integrable?
Yes, sir.
Need not, sir.
You should be careful. You should be careful. Yes, because here you are integrating over a set of finite measure. Right? So basically what we are going to use is that a constant function is integrable over a set of finite measure. Okay, so that's what we are going to use. So let modulus of fn of x less than or equal to m almost everywhere on E. This is given to you. I am going to define g of x as m for every x in E. For every x in E. Then I have mod fn x is less than or equal to g almost everywhere. And now I can use Lebesgue dominated convergence theorem, provided I know that g is integrable. Okay, now integral over E g dm is equal to integral over E g is constant function m dm, and for constant function the integral is m times the measure of the set over which you are integrating, and you know that measure of E is finite, so this is less than infinity. That means G is integrable. Therefore, G is integrable. So what we have observed is that a constant function on a finite measure set is integrable. Now apply. Now we can apply DCT and get the conclusion. That's it. As I told, it's a special case of DCT, but I just wanted to record this so that the statement at least will be available to you without referring to any book. Okay. So just for a comparison, what we had so far is key theorems in Lebesgue integration theory. We discussed the following key theorems. And what are those theorems? To name them, Fartu's lemma, monotone convergence theorem, bounded convergence theorem, and dominated convergence theorem. All these theorems are prefixed with the name Lebesgue, Lebesgue dominated convergence theorem, Lebesgue bounded convergence theorem, and so on. And if you closely observe essentially, the commonality between all these theorems is that it addresses same question. It addresses same question. And what is that question addressed by all these theorem? If you have a sequence of measurable functions, each of which is integrable, and suppose the functions, the sequence converges pointwise to a function, whether that pointwise limit is integrable and whether integral of the limit is equal to limit of the integral. Okay, so let me write, though it may be repetition, all these theorems addresses the following question. And what is that question? If Fn is a sequence of measurable functions, measurability is a minimum assumption for integrability that converges almost everywhere to F, then question is this: can we assert something about integral F? I'm not writing a precise question, but this is what basically it does. And this is what you should keep in mind about what are all these various theorems about. Precise statement, etc. comes later. We assert something about integral f dm in terms of integral fn dm under suitable hypothesis. This is what the question is. Again, for a quick recall, let me tell you that among all these theorems, Fato's lemma, monotone convergence theorem, etc., the hypothesis is weakest in Fato's lemma. And obviously, the conclusion is also weakest. Okay. Even I will write it in the same manner. Note that Fato's lemma has the weakest hypothesis. Can you remind me what was the hypothesis in Fato's lemma? Can anyone remind me what is the hypothesis?
Non-negative measurable functions.
Pardon? Measurability is
non-negative
measurability is anyway there. Yeah. Apart from measurability, is there any condition? Yes.
Non-negativity.
So non-negative measurable.
Non-negative. In other words, you can say that the elements in the sequence are bounded below by 0. Each Fn is greater than or equal to 0. So bounded below by 0. So we need only have Fn is bounded below by 0. And then Fato's lemma with our assumption. I already told that Fn converges almost everywhere to F in the question, if you see. Okay. So in that case, the Fato's lemma says that Fathus lemma asserts integral f dm is less than or equal to limit infimum integral fn dm. But if you observe, if you recall, the Fathus lemma doesn't require even the convergence. It is not talking about the sequence of functions fn that converges pointwise to f. Since I wrote the question in the manner that fn converges to f almost everywhere, if you see. So this is how I wrote the question. Okay. With that assumption, Fathus lemma says that integral f dm is less than or equal to limit infimum integral f and dm. But in fact, Fathus lemma so you see the conclusion is also weakest. It is not equal to. It says only less than or equal to. In fact, further, Fathus lemma does not require fn converges to f almost everywhere. And the conclusion in that case, is that integral limit infimum fn dm is less than or equal to limit infimum integral fn dm. So I just wanted to highlight the fact that Fathus lemma has the weakest hypothesis among all these theorems, and obviously it has correspondingly the weakest conclusion. Okay, it is not equation, it is now inequality. Now coming to next theorem, let us say bounded convergence theorem. Okay. In bounded convergence theorem, the hypotheses are each function is bounded above and below by a constant. Modulus of fnx less than or equal to m. Okay. Fn's are bounded above and below by constants. Let us say small m and capital M. Small m less than or equal to f of x less than or equal to capital M. Okay, and then you can obviously write it in the form modulus of fnx less than or equal to some k. Okay, so in Fathus lemma you want only to be bounded below by 0. Here you want both bounded above and below by some number, by suitable number. Okay, and that's the thing that you want, and then it's assert that integral f dm. The conclusion is this is equal to limit integral f and dm. So you have the relatively stronger conclusion in terms of equality, not just inequality. Okay, and in monotone convergence theorem, you have an additional assumption that the sequence are monotonically increasing. In MCT, FNs are monotonically increasing. And we have seen we cannot handle monotonically decreasing. Okay, and the grand theorem in the area is Lebesgue dominated convergence theorem. Okay, and if you see, it doesn't require non-negativity assumption. It doesn't require monotonically increasing assumption. It doesn't require bounded by a constant. And it doesn't require the measure to be finite. That is important in bounded convergence theorem. Okay, Fn's are bounded above and below by constant, and they are defined on set of finite measure. Set of finite measure. That is important. So none of these hypotheses is needed in dominated convergence theorem. I repeat, there is no need of monotonically increasing. There is no need of set to be of finite measure. There is no need of bounded above and below by constant. There is no need of non-negativity. All these hypothesis is replaced by a single hypothesis. Namely, the function is bounded above and below by integrable functions. Okay, all the functions in the sequence is dominated by a integrable functions. Okay, so let me write down that in DCT. This comparison will help you to remember. In DCT, hypothesis does not require sequence to be non-negative. It does not require sequence to be monotonic increasing. It does not require measure on the set on which all these functions are defined is finite. All these assumptions are replaced by a single hypothesis or single assumption. And what is that assumption? Each function in the sequence is bounded above and below by integrable functions. See, okay? It should be uniformly bounded above and below. That is, irrespective of n, you should be able to get one function that bounded above and one function that bound below. Okay. Single assumptions, namely G1 less than or equal to Fn less than or equal to G2 almost everywhere for every. I wrote in terms of mod Fn less than or equal to G, but once you have two functions G1 and G2 integrable and G1 less than or equal to Fn less than or equal to G2, you can take maximum of G1 and G2 and write in that form. That's not a big deal. Okay. Where G1, G2 are integrable. But what is important is it should not depend on n. So far, so good. So till now, we have not done anything new. I was just trying to compare various theorems so that this will be, clear in your mind, all these hypotheses. Is that okay?
Yes, sir.
So with this, we shall conclude about various convergence theorem that we want to discuss in Lebesgue integration. But once again, if you recall the progress in the course, I was commenting quite often that Lebesgue's study on measure and integration is mainly motivated by Raymond's theory of integration, and he wanted to remove all the shortcomings that Raymond's integration theory had. Okay, if not all, at least the important shortcomings or the serious shortcomings of Raymond's integration theory, he want to remove. Okay. So once again, let us try to relate Rayman integration and Lebesgue integration. Okay. We already proved that in case a function is Rayman integrable, then it will be Lebesgue integrable, and Rayman integral and Lebesgue integral will coincide. We have proved. Yes or no?
Yes,
Yes,
sir.
sir.
But not completely. I have done it only for non-negative function. Do you agree?
Yes, sir.
So now the question is it in general true for any type of function? That is one question. And second question is there some other relationship between Rayman integral and Lebesgue integration? So those things we shall explore now. So once again, we are back to relation between Rayman integration and Lebesgue integration. Okay. So let me note down here that we already observed that if f is a function from AB subset of R to non-negative 0 infinity. Infinity you cannot include if you want to talk about Rayman integration, because Rayman integration basically deals with bounded functions. Okay, is a bounded function, bounded Rayman integrable function. Then it is Lebesgue integrable and integral a to b f of x dx. When I write like this, I mean it Rayman integration is equal to integral over ab f dm. This we have proved for a non-negative function. Okay, so now we shall observe that this is true not only for non-negative function, it is true for any Rayman integrable function. Okay. Now we shall observe that this result is true for any Rayman integrable function and in fact we will have a bonus. Not only that we will prove every Rayman integrable function is Lebesgue integrable, we shall prove something extra. Okay, what is that something extra that we are going to prove? In order to motivate it, let me start with the following. Okay, I hope all of you know that every continuous function is Riemann integrable. Do you
Yes, sir.
recall that? Recall that every continuous function. Of course, when we talk about Riemann integration, we are dealing only with functions that are defined on closed bounded interval. Every continuous function f from AB to R is Riemann integrable. Perhaps this would be the first class of functions that you might have proved to be Riemann integrable. Continuous functions are Riemann integrable. You might have also seen that if a function has finite number of discontinuity on an interval AB, then also the function is Riemann integrable. That can be easily handled. Okay. Did you do that in your B.sc course? Further, yes or no? If f from AB to R has a finite number of discontinuity, then f is Riemann integrable. Intuitively, you can understand like this. Suppose it has finite number of discontinuity x1, x2, and so on. You can split the integration into several a times x1, then x1 times x2, and so on. Finite number of integrals, and then you can integrate. Is that okay?
Yes, sir.
Now, in the next level, so first continuous case are Riemann integrable. Finite number of discontinuity case is also Riemann integrable. In the next level, perhaps you might have seen this example. If not, please try to fill the details. Okay, I am just hinting at the example. The function is popularly known as Thomas function. Define the function as follows. F from, let us say, 0, 1 to R. F of x, I am defining like this. 1 by Q if x is a rational number in 0, 1. X is of the form, once it is rational, it can be written in the form P by Q, where P and Q are in lowest term. Okay, GCD of P and Q is 1. So if it is rational, x is rational, I will define f of x as 1 by q. 0 in the irrational points. If. And at x equal to 0, I will define it as 1. 1 if x is equal to 0. So this is my definition. 1 if x equal to 0 is not of that important. You can define it to be 0 at x equal to 0 as well. So it doesn't matter. So this is the way in which the function is defined. This is so-called the Thomas function. And do you know something about its continuity from your course in real analysis?
It is continuous.
Continuous verb.
Continuous on to
Continuous
complement
at, not audible. Nidin wanted to say something. Continuous at. Okay, let me tell you. This function is continuous at all irrational points and discontinuous at all rational points. Okay? This function, try to see it. Okay, this function is continuous at all irrational points in 0, 1 and discontinuous at all rational points. Thus, if you collect the set of discontinuities, set of points at which the function is discontinuous, it is countable. Okay, thus f has countable number of discontinuous points. Better way to say is set of points where f is discontinuous, it's countable. Okay. Now, though it is not relevant to us, you might have seen the fact that you can ask the reverse question. Can I have a function which is continuous at all rational points and discontinuous at all irrational points? Have you come across such a question?
Yes, sir.
Yes.
Yes, sir.
And it's not possible. And that's a consequence of Bayes' category theorem. Do you know what is Bayes' category theorem? Okay, so those are not our subject matter for the time being. So let me stop with this example. So we have this example, and what happens at this example is that the function is continuous at all irrational point and discontinuous at all rational point. I just wanted to remind you is that the converse situation, that is a function having discontinuity exactly at irrational point, that's not possible. Such a function does not exist, and that is a consequence of Bayes' category theorem. So that is not our subject. Now let us go back. Continuous functions are integrable. If a function has finite number of discontinuity, then it is integrable. Here you have infinite number of discontinuity. However, the set of discontinuity is countable, and also using the definition you can prove that this function is Riemann integrable. Okay, try also to do that. Further, this function is Riemann integrable. Okay, and last in that progress, I put f of x to be equal to 1 when x is rational in 0, 1 and -1 when x is irrational in 0, 1. This is a famous function, so-called Dirichlet function, and I hope you know about the continuity. This function is nowhere continuous, then f is not continuous at any point on 0, 1. So it has uncountable number of discontinuities. Okay, uncountable number of discontinuity. And do you know something about its Riemann integration? And that we have recalled in first week of our course.
It is
What
not
can you say
Riemann.
about Riemann? It is not Riemann integrable. Further, this function is not Riemann integrable. Okay. So all these examples I gave so that you will get a feel. What is that feel that I want you to get? It is the following. Suppose you consider the first remark that I have written. Every continuous function is Riemann integrable. Next, if it is discontinuous at finite number of points only, then also it is Riemann integrable. In the next example, I have functions which are discontinuous at infinite number of points, but still it is Riemann integrable. So discontinuity at infinite number of points may not create an issue for Riemann integrability. Whereas the last example, it is discontinuous everywhere and it is not Riemann integrable. So at least these examples should convince you that there is some relationship between Riemann integrability and, can you complete my statement? There is some relationship between Riemann integrability and
Point of
what?
discontinuity.
Number of points of discontinuity. Okay, so let me write it down. And the question is, what is the exact relationship? Okay. Therefore, we smell the following. Therefore, there is some relationship between Riemann integrability and the nature of the set of discontinuity of a function. In fact, the nature of set of discontinuity determines whether a function is integrable or not, Riemann integrable or not. Okay, as I told you, we want to make the exact statement. What is that relationship and prove it? Okay, the statement is a part of a beautiful result that combines Riemann's integration theory and Lebesgue ideas. Okay, and that is normally called Riemann-Lebesgue theorem. So I will not state the theorem now because I have to do some more things to prove that theorem. So let me do those things and then state and prove the theorem. But let me just pronounce the theorem. The theorem is as follows. A function defined on AB, bounded function, is Riemann integrable if and only if set of discontinuity is of Lebesgue measure 0. I repeat, a function defined on a closed bounded interval is Riemann integrable if and only if the measure of set of discontinuity is 0. When I say measure, I mean the Lebesgue measure. Okay. In other words, the function is continuous almost everywhere. Where it is discontinuous is of measure 0. In other words, it is continuous almost everywhere. Okay. For instance, if you see this example, 1 by q and so on, where it is discontinuous is at rational points and set of rational is countable and countable set is of measure 0. Yes or no?
Yes, sir.
Therefore,
Yes, sir.
the Thome function is continuous almost everywhere. Thome function is continuous almost everywhere. Whereas if you pass to Dirichlet function, what happens is that Dirichlet function is discontinuous everywhere. Okay, so set of points of discontinuities is entire 0, 1 and 0, 1 is not of measure 0. In fact, the measure of interval 0, 1 is 1. Okay. So before stating the theorem which I have orally told, let us do some more things and then we will state and prove the theorem. But the theorem should be kept in your mind. The theorem statement runs as follows. A function is Riemann integrable if and only if set of discontinuity is of measure 0. In other words, the function is almost everywhere contiguous. So that is the famous, and I feel it very beautiful theorem in the sense that it combines two different areas, two different theories. One is Riemann theory of integration and the other is Lebesgue measure theory. And it is not proved by Riemann, it is proved by Lebesgue. Let F from AB to R. Let us do some more observations about Riemann integration. P bounded. And for Riemann integration, everything depends upon the partition, etc. You know. So let us start with partition. I will be quick with all this discussion. My main aim is to state and prove that result. Let P be a partition of AB. Let us say P is equal to A is equal to X0, X1, X2, so on. Xn is equal to B with X0 less than, X1 less than, X2 less than, and so on and so forth, Xn. So let us quickly recall the Riemann theory, of course, with not full details, whatever we want. Okay. Now what we do is you define capital Mi and small mi. Capital Mi is supremum of f of x. Okay. I will define it over xi minus 1 less than or equal to x less than or less than xi. Okay. Intentionally, I avoided xi. Okay. And small mi is equal to infimum of f of x. These things will not make big difference. Xi minus 1. Usually we put less than or equal to x, less than or equal to xi. I will just put less than xi. Okay. This is how I define supremum and infimum. Now what I will do is to define step function. I wanted to view Riemann via Lebesgue. Define step functions alpha and beta as follows. So each subinterval, I will put alpha to be capital Mi. Alpha of x is equal to Mi for xi minus 1 less than or equal to x less than xi. And similarly, beta of x I will define as small mi for xi minus 1 less than or equal to x less than xi. So you have a b here. Okay. A is x0, b is xn. So you have defined it from x0 to x1. Then x1 to x2, x2 excluded. Then x2 to x3, x3 excluded, and so on. So you can see that finally at the xn, you have not defined your alpha and beta. Sorry, at xn, the last extreme point, you have not defined alpha and beta. There you can define as you wish. Okay, so at endpoints, endpoint means the B, endpoint B, we define alpha B and beta B arbitrarily, maybe put 0. So that now alpha and beta are defined for all x in AB. Okay. Now, do you see that alpha and beta are Lebesgue measurable?
Yes, sir.
How does it follow? Because they are
Simple function.
step functions and each step, each mi is over an interval, and intervals are measurable. Okay. Note that alpha comma beta are measurable. Okay. Now, let me also remind you that for the integration theory, Lebesgue integration theory, which we have developed only on R so far, all these things can be done in abstract setting. That will be content of one lecture, forthcoming lecture. That all these things we can do in general sigma algebra and general measure space. With the general measure, need not be with the Lebesgue measure. Okay. However, what now I wanted to point out that for a integration theory, what you want is the following. You want a measure space to start with. And for a measure space, you need a set, you need a sigma algebra, and you need a measure. And Lebesgue integration is over the following measure space, namely R, sigma algebra of all Lebesgue measurable set and Lebesgue measure. So that you should keep in mind. Bear in mind that for Lebesgue integration theory, we have the following. We have the measure space. We have the measure space R, M, M, where M is the sigma algebra of all measurable sets, Lebesgue measurable subsets of R. And M is Lebesgue countermeasure restricted to M. M star restricted to M. The Lebesgue measure. This is just to remind you that this thing is a basic setting that you want for integration theory. Is that okay?
Yes.
Yes, sir.
I just doubt whether there is some lag.
Yes,
Can
sir.
you hear me properly? Can you
There
hear
is
me
some
No,
properly?
sir,
lag.
there is no lag.
Pardon?
There is some lag.
So are you able to hear me properly, or it's an obstruction to the lecture? So let me just
You can hear after 1 minute or something.
okay. So let me give me a moment. Let me try with another inter Okay, sorry for the inconvenience caused. I think now it will be better. Okay. Can you hear me?
Yes.
Yes, sir.
Yes, sir.
So this thing I want you to keep in mind, because that will help also in future classes. Whenever you discuss an integration theory, the basic setting that we need is a measure space. And in the Lebesgue integration on R, the measure space that we have is R, M, M. And what is scriptium? It is the collection, sigma algebra of all Lebesgue measurable sets. And small m is the Lebesgue measure. And then you are integrating over R. You are integrating measurable functions over R. Okay. Now, if you want integration over subset E, there are two ways to do it. I repeat, if you want integration not on entire R, but you want on E, there are two ways to do it. The easiest way is, can somebody tell me? Instead of integrating over R, you integrate over, sorry, instead of integrating over E, you integrate over R. Not the
R.
same function, but which function?
The function integrated with characteristic function.
Yeah. So integration over E, you will define as integration over R. If you want integration of F, instead you integrate chi F. So that you don't need any new measure space. Again, you can work with R, M and M. That is one thing. Or what you can do is, okay, you consider E. If you want to integrate over E, you consider the measure space E, M dash and small m dash. Okay. So now can you tell me what will be script m dash?
The set of all
Restriction.
measurable.
Yeah. Collection of all measurable sets, measurable in R, which are subsets of E. Which are subsets of E. Okay. So m dash would be is equal to collection of all E subset E, not E, I will not write, E already used, collection of all A, collection of all A Lebesgue measurable, and A subsets of E. You consider only those Lebesgue measurable set which are inside E. Okay. So like that also you can proceed. And m dash is obviously again m dash the restriction of Lebesgue measure on script m dash. Okay. So like that also you can proceed. Okay. Why I am saying all these things is just to targeting what we are going to do in the next future classes. And also, since we are talking about Lebesgue integration, you want integral over AB, not integral over R. Okay. So anyway, so please keep in mind that for the integration theory, you need a measure space. Let us now continue. We have seen that alpha and beta are measurable. Okay. Now, let us try to find integral over AB, integral over AB, alpha dm. Since you want integral over AB, you should worry about the measure space with AB as the underlying set. Or you can go to R and instead of integrating alpha, you integrate chi e alpha. Anyway, this is equal to integral over AB. What is alpha? Alpha is defined as a step function. Alpha of x is equal to mi in this interval. Okay, so alpha will take the form summation I is equal to 1 to n capital Mi chi xi minus 1 xi. I don't bother how it is defined at the extreme point D. And for this integral, you know, it is a simple function. So integral would be summation I is equal to 1 to n mi measure of xi minus 1 xi. Everything is inside AB. And since this is an interval, measure is length. Summation I is equal to 1 to n capital Mi length of this interval xi minus 1. This is the integral of alpha. Similarly, Lebesgue integral of beta would be, I'm not writing the detail, summation I is equal to 1 to n small mi xi minus 1. So we define step functions alpha and beta starting with the Riemann integration process, and then we have calculated Lebesgue integral of alpha and beta. It makes sense because alpha and beta are step function. In particular, they are measurable. Okay. Now, you look at the right hand side of integral alpha, Lebesgue integral alpha dm. Look at the right hand side. What is it actually in the language of Riemann integration? Is the question clear? Look at the RHS of integral alpha dm. Can you identify that quantity in the language of Riemann integration? What is it?
Sum.
Upper Riemann integration.
Upper, not integration, upper Riemann sum. Okay. This is equal to UPF. Upper integral is different. This is UPF. That is upper Riemann sum corresponding to this partition. Riemann sum in the language of Riemann integration. Riemann integration. Similarly, integral beta dm would be lower Riemann sum of f corresponding to the partition, which is lower Riemann sum. Okay, so this is one observation. Upper Riemann sum and lower Riemann sum can be identified as Lebesgue integral of step functions. Okay. Now, instead of taking one partition, let me take a sequence of partition Pk. Let Pk be a sequence of partition such that Pk plus 1 is a refinement of Pk, such that you know what is the refinement means. You just adjoin some more points. To get Pk plus 1 from Pk, keep all points in Pk and adjoin some more points. Okay. Such that Pk plus 1 is a refinement of Pk. That is, Pk is contained in Pk plus 1. And further, and let us also assume that norm of Pk or mesh length of Pk is tending to 0. And what is norm Pk? If you remember the Riemann integration theory, norm Pk means the length of largest subinterval determined by partition Pk, where norm Pk is the length of Pk is a partition, so whole interval will divide into several subinterval. Consider length of those subintervals and take the maximum. Length of largest subinterval determined by pk. Okay, so now whatever you have done with a single partition P, that is defining step function alpha beta and identifying integral alpha as Riemann sum and so on, you can do for each partition Pk. So let me write the corresponding notation as alpha k and beta k. Let alpha k and beta k be functions defined previously, defined earlier, that is alpha and beta, with respect to, but with respect to not P, Pk. Is that okay?
Yes, sir.
Now, whatever you did with single partition P, you do for each partition Pk, so that you will get step functions alpha k, step functions beta k. Now, can you tell me what is the connection between alpha 1, alpha 2, alpha 3 and so on? I mean, can you compare? One will be greater than, less than, etc. Look at Pk and Pk plus 1. If Pk is this, if Pk is this, Pk plus 1 would be that, possibly some points are more. So let us say x star here, something more, maybe x star star here, something more, and so on. This is Pk plus 1. Keep this picture in mind and now tell me what is the relationship that you find between alpha 1, alpha 2, alpha 3 and so on.
So alpha k decreasing and beta k increasing.
Then, so let me just write alpha 1 greater than or equal to alpha 2 greater than or equal to alpha 3, etc. And each of them would be greater than or equal to f, because you are taking in each subinterval mk, capital Mk, which is supremum. So do you agree this?
Yes, sir.
And similarly, if you compare beta 1 will be less than or equal to beta 2, less than or equal to beta 3, etc. And all of them will be less than or equal to f. So alpha also will be, alpha case will be monotonic increasing, beta case will be monotonic increasing, and f will be sandwiched between them. Thus, alpha k is a decreasing sequence, and each alpha k is measurable, decreasing sequence of measurable function. And beta k is an increasing sequence of measurable function. Since it is decreasing sequence and increasing sequence, you can talk about it limit. And in this case, limit will be not infinity or minus infinity, because even though it is increasing and decreasing, it is all bounded by f. Okay. Therefore, you can talk about limit. So let limit alpha j of x, I call by something. Let me put it as alpha of x. But this alpha is different from the alpha that I have told in the beginning. Okay. That is for a single partition. And similarly, define limit of beta jx to be, let us say, beta x. Is that okay? Why this limit exists?
Because they are bounded functions.
They are all increasing and decreasing, and they are bounded above or below by f. Okay. Thus, so this limit exists. Okay. And remember, f is bounded. because we are talking about Riemann integration, and the basic assumption for Riemann integration is bounded. F is bounded. Since F is bounded, say modulus of f of x is less than or equal to, let us say, some k. We have modulus of alpha k is less than or equal to k, and modulus of beta k, this k and this k is different. Okay, this is capital K, constant k, is less than or equal to k for all k. Or I can write alpha j less than or equal to k, and that follows again from this, where capital K is a constant. So now you have a sequence alpha case of measurable function, beta case of measurable functions. They are pointwise convergent, and each of the alpha k is dominated by a constant. So where are you heading to?
Bounded convergence theorem.
Bounded convergence theorem or dominated convergence theorem. Therefore, applying bounded convergence theorem, integral alpha k dm over AB will converge to alpha k converges to alpha. Okay, integral alpha dm over AB, and integral beta k dm AB converges to integral over AB beta dm. Okay, now go back and see what is alpha k. Alpha k is the step functions, that is UPF. For a single alpha, integral alpha dm is identified as UPF. Okay, so what is integral alpha k dm? It is UPKF. Do you agree? This is upper Riemann sum corresponding to partition Pk. I am talking about integral alpha k dm. And integral beta k dm is lower Riemann sums corresponding to partition Pk. Yes or no?
Yes, sir.
Yes, sir.
And upper Riemann sums, since Pk is a refinement partition, as norm Pk tends to 0, the upper Riemann sums converge to what in Riemann's theory? Upper Riemann sums converges to what? Upper Riemann
Integral of
integral. It converges to upper Riemann integral. And lower Riemann sums converges to what?
lower Riemann integral.
Lower Riemann integral. That means integral alpha dm is upper Riemann integral and integral beta dm is
Lower Riemann integral.
lower Riemann integral. But this is Riemann integration theory, okay? But integral AB alpha k dm is equal to UPKF, that we have seen, and UPKF converges to upper Riemann integral, integral A to B f dx. Similarly, integral AB beta k dm, we identified that this is equal to lower Riemann sum LPKF, but we know that lower Riemann sum LPKF converges to lower Riemann integral. Riemann integral. Integral a to b f of x dx as norm pk tends to 0. Okay. Therefore, if f is Riemann integrable, we say that f is Riemann integrable. Riemann integration definition is function is Riemann integrable if and only if upper Riemann integral and lower Riemann integral coincides. But that will happen now due to our observation. That will happen if and only if the Lebesgue integral of alpha coincides with Lebesgue integral of beta. Is that okay? Because upper integral is Lebesgue integral of alpha. Is that okay? We have not done something great. We are just trying to connect Riemann integration theory with the Lebesgue integration. As time is up, the next thing what I wanted to do, I will put as an exercise. It's not hard. It is just usual epsilon delta argument. Okay. If x is an element in AB, x is a point in AB, and it is not an endpoint, not the endpoint of any interval determined by pk. Pk is a partition as I have put above k in n. So suppose x is not endpoint of the subinterval determined by the partition pk. Then the exercise demands you to prove that f is continuous at x if and only if the following happen. If and only if alpha x coincides with f of x coincides with beta of x. You can try to do this as an exercise. As I told, it's not hard. It is just usual epsilon delta argument with the definition of alpha and beta in your hand. Okay. So now, for a particular pk, how many such x's are there? What is x? It is not the endpoint. It is not the endpoint. So for a particular pk, how many such x's are there?
Uncountably many.
X is how many endpoints are there? I will ask endpoints. Finite number, right? Finite number. So if you take all pk's, at most there are countable number of endpoints. At most there are countable number of endpoints. In the rest of the point, you have this continuity criterion. F is continuous at x if and only if alpha. So except at countable number of points, you have this continuity condition. Is that okay?
Yes, sir.
Now we have the main theorem. So this exercise you please do. And the theorem now the proof will be based on this exercise. This is the beautiful theorem that I was talking about, which is also called Riemann-Lebesgue theorem. So some people call Lebesgue criterion for Riemann integrability. Let f from AB to R be bounded. Then first part of the theorem says a necessary and sufficient condition for Riemann integrability. F is Riemann integrable. F is Riemann integrable if and only if f is continuous almost everywhere on AB. Though you know the meaning of almost everywhere, let me write it. Or, in other words, set of points of discontinuity. Set of points of discontinuity of F is of measure 0. Is of measure 0. So through example, we smelled that there is some relationship between Riemann integrability and nature of the set of discontinuity. And what is that relation is this. A function is Riemann integrable if and only if set of points of discontinuity has Lebesgue measure 0. Okay. And in particular, if a function has countable number of discontinuity, it will be Riemann integrable. Okay. Further, the second part of the theorem says that in that case, suppose f is Riemann integrable. In that case, f is measurable. F becomes measurable. Once it is measurable, it is the basic condition required for Lebesgue integration. Now you can start thinking of Lebesgue integration of F. And Lebesgue integration of F coincides with Riemann integration of F. So you have measurability automatically from Riemann integrability. That's what theorem says. Once you have measurability, you are in a position to think of Lebesgue integration. And what theorem says that Lebesgue integration will coincide with Riemann integration. Here there is no assumption of non-negativity. We have proved this result for non-negativity only. Okay. And what is more important is first part. Necessary and sufficient condition for Riemann integration. Okay. So I will give you a quick proof. Give me 2-3 minutes. The proof will be based on the discussion that we had so far about Riemann integration. How upper sum, lower sum, etc. we identified with the Lebesgue integration and all these things, and also based on the exercise that F is continuous at X if and only if all these things coincides. Okay. So based on that, the proof is just simple. So assuming you can complete the exercise, let me try to write the proof. Assume F is Riemann integrable for one part. F is Riemann integrable. Okay. Then what we know is that upper Riemann integral coincide with the lower Riemann integral. But upper Riemann integral we identified as integral alpha dm. Then integral alpha dm is equal to integral beta dm. Do you agree?
Yes.
That is what our discussion shows. Upper Riemann integral and lower Riemann integral coincide, but upper Riemann integral can be identified with integral alpha dm. Okay. Also recall that alpha 1 is greater than or equal to alpha 2 greater than or equal to etc. All are greater than or equal to f, and they are all greater than or equal to betas. Beta 2 greater than or equal to beta 1. This we observed with alpha k, beta k, etc. with the original meaning that we have in the discussion. And this implies integral over AB alpha minus beta dm is equal to 0. Integral alpha dm is equal to integral beta dm. That implies integral over AB alpha minus beta dm is 0. Okay. And please note that alpha minus beta is non-negative. That is because of this. Okay. So let me write that also. Before this, let me write that since this alpha beta relationship you have, you can observe that thus alpha of x is greater than or equal to f of x is greater than or equal to beta x. Each alpha k is greater than or equal to each of the beta k. Now you pass it to the limit. Alpha is limit of alpha k, beta is limit of beta k. So you will get this. Is that okay?
Yes, sir.
Because alpha case are greater than f and beta case are less than f. And alpha case converges to alpha. Beta case converges to beta. From that you will get this. So now you take this. We have integral alpha dm is equal to integral beta dm. And therefore, integral over AB alpha minus beta dm, give me 2 more minutes, is equal to 0. Okay. So you have integral is 0 and integrand is non-negative. Integral is 0. And what is integrand? Integrand is alpha minus beta. And I have observed that alpha of x is greater than or equal to beta of x. Therefore, alpha is greater than or equal to beta. Therefore, alpha minus beta is non-negative. The integral is 0 and integrand is non-negative will imply, I don't know whether I have proved it or not. If I have proved, well and good. If I have not proved, it is easy to see that this integral equal to 0 will imply alpha minus beta equal to 0. Not everywhere, almost everywhere. So what the result I am using is, if a function is non-negative and its Lebesgue integral is 0, the function will be 0 almost everywhere. Did I prove it? I
Yes,
forgot.
sir.
I have proved it. Okay. Integral f dm is equal to 0. F greater than or equal to 0 implies integral f equal to 0 almost everywhere. Okay. And that implies alpha is equal to beta almost everywhere. Alpha is equal to beta almost everywhere. That means except on a set of finite measure, alpha is equal to beta. But if alpha is equal to beta, everything will coincide with the fx. Yes or no?
Yes, sir.
Because f is between alpha and beta coincide. So everything will coincide with f. Thus, except on a set of finite measure, alpha is equal to beta is equal to f. Now go to the exercise. What's the exercise that I have given? If alpha of x equal to f of x equal to beta x, then f is
Continuous, sir.
continuous. Okay, so you can see that except on a set of finite measure, f will be continuous. Okay, thus via exercise, you have to spend some time, I know, but this is the outline. Thus via exercise, we conclude that f is continuous almost everywhere. So thus, if it is Riemann integrable, it is continuous almost everywhere. Now converse, again it is very simple converse. F is continuous almost everywhere. That will imply, again exercise, f is continuous almost everywhere means at those points alpha will be equal to beta will be equal to f of x almost everywhere. And that will imply integral alpha minus beta dm is equal to 0. If the functions are equal almost everywhere, the integral is same. And that will imply integral over alpha dm is equal to integral over beta dm. And that implies the upper Riemann integral is equal to lower Riemann integral. That implies f is Riemann integral. Okay. So this is quite easily done. Second part, I don't wanted to trouble you both more. Second part is also obvious. You try. The second part is f measurable. F is measurable and integral f dm is equal to integral Lebesgue integral is equal to Riemann integral. That's now easy, just 1 or 2 steps. I will write down it, and while uploading, I will just write down those part also. But you can do it yourself. Okay. Measurability, is it clear? Because suppose f is Riemann integrable, then alpha of x is equal to f of x equal to beta x almost everywhere. And do you know alpha and beta are measurable? Am I going fast? Is alpha and beta measurable? What is alpha? Limit of alpha case. And alpha case are step functions. So alpha case are measurable. Therefore, alpha is measurable. Beta case are measurable. Therefore, beta is measurable. So alpha and beta are measurable. Further, if it is Riemann integrable, then you have seen that it is continuous almost everywhere. Therefore, alpha of x will be f of x equal to beta x almost everywhere. Are you getting me?
Yes,
Yes,
sir.
sir.
So once alpha of x equal to f of x equal to beta x almost everywhere, and alpha is measurable, what can you say about f?
F is measurable.
Measurable. So that is the beginning of the second part. F is measurable. Okay. Then you prove this. Now I don't want to trouble you both more. I will just write the proof and upload it in the PDF. I don't wanted to again go back to this relationship, Riemann and Lebesgue. The next day I will start with a new topic. Okay. Thank you.